Hello everybody, welcome back to this lecture series on linear systems theory. So, we still continue with our lectures on linear algebra. So, last time what we saw was about how a linear transformation is essentially defined by a matrix. So if I had a transformation, say let me call this say A from a vector space U to another vector space V. So, this is A essentially had a matrix kind of structure. Okay. Now, we will do a little bit on the structure of this matrix, and if it has some more information that we can exploit for ourselves. Okay. So let's start by building. So, let's assume that I have a matrix A which is of dimension m cross n. It could also be square, but we will just do a more general case of m cross n and matrices. So, we will define what is known as the column space, the null space, the row space, and also the left null space or the kernel of the transpose. And what these mean are possibly clear by their name, but we will do a bit of their details. So, based on which of these are do they belong to the set 1, 2, 3 or 4, they can either be of dimension Rm or dimension Rn. Okay. And for n cross n, it's a little bit simpler. Everybody will belong. So, all these fundamental subspaces will be subsets of or subspaces of Rn. Okay. So, first about the column space. So, as the name suggests, it is a vector subspace spanned by the columns of the matrix, right, and C of A is then a vector space with the columns of A as its basis. And if you look at it carefully, this also has close connection with the definition of the image of a linear map. So, what do this mean? So, if I have an M cross n matrix, the column space comprises all vectors C equal to Ax, well first such that C of A, which is the column space, is the span of all these columns of A. So, this is the first column of A, second column of A until you have n columns. So, you have a M cross n matrix. Alternatively, C of A is all the vectors C which satisfy C equal to Ax for all x coming from Rn. So, your map again is from so this map, if I look at A, is from Rn to Rm. Okay. Now, this C of A, so if I just take say the C of A gives me elements in the space M, right. So, in the space Rm, and therefore, C of A is a subspace of Rm, right, because you are looking at C of A means, so I am already over here. Okay. And the dimension of this C of A is at most the minimum of these either M or N. So, so that depends really if you know if M is greater than N or if M is less than N or so on. So, let us say I take a matrix which is say 4 cross 5. So, this will have 5 rows, right. So, I have A C1, A C2, A C3, A C4, A C5, right. So, these 5 vectors, at most I can have vectors which are 4 vectors which are independent of each other. So, whenever I have a dimension this way, there will always be the 5th vector which I can write as a combination of the other 4. So, at most I can have 4 independent column vectors, right. So, similarly even if I have a 5 cross 4 matrix, right. So, I will have A C1 till A C4. So, at best I can still have 4 independent column vectors. I can have 3, 2, 1 and nothing also if it is just the 0 matrix. Okay. So, similarly the null space is the vector space generated by the set of vectors x such that Ax equal to 0, very similar to the definition of a kernel. So, I am looking at all x such that Ax is equal to 0, right. So, if I take the all of these x, then it will be a subspace of Rn, because I am just looking at these x's, whereas in the previous case I was looking at C, which is actually A of x or A times x, which belongs to the range space, and this belongs to the domain. Okay. So, like what does this mean, like practically? So an A consists of all the vectors. Say maybe I can start with some vectors here, which just under this transformation A just go to the 0 element here, or they just lose their identity, or they are vectors of dimension 0, right. So, that is about the column space of A or C of A, or the null space of a transformation which is denoted by the matrix A. Similarly, I can also define what is a row space. Now, it should be kind of obvious by what we defined earlier, right. So the R of A consists of all possible linear combinations of rows of A. Okay. So, if I look at the matrix representation, again starting from n m cross n matrix, the row space comprises all the vectors. So, so if I just have these rows, right. So, I have 1, 2, 3, 4 and so on up to m number of rows. I am just looking at the span of all this of these row vectors. So, I just look at the transpose, because usually I talk of, when I talk of a basis vector, I usually talk in terms of the columns. So, I just look at the row vectors and the span of it, essentially the transpose of the row vectors, or in other words, this can also be considered as C of A transpose is the same as R of A, right. Okay. So, what is R of A now? R of A will be now a subspace of Rn because of this, right. So, what is R of A? All R's such that A transpose of Y will be equal to R. So, if A is of dimension m cross n, then I am looking at A transpose of dimension n cross m, and therefore, the range space is now a subspace of Rn, right. And this can also, as I said earlier, can also be considered as the image or the range of the A transpose. Okay. Now, the last definition in this set is the left null space. So, well, again as the name suggests, so the right null space, if I just look at, I am looking at A times x equal to 0, right. So, here I am looking at A transpose of y equal to 0. So, the null space of A transpose is all y which come from Rm such that A transpose of y equal to 0. Again, so these y's are in Rm, therefore, the entire set, if I construct it, will be a subspace of Rm, right. So, alternatively, loosely speaking, this contains of all the vectors that lose their identity when mapped from Rm to Rn via A transpose. So, just if A is a mapping, so this is an m cross n going from Rn to Rm, then A transpose would simply be a map from R of m to Rn. Okay. So, this is pretty basic, right, just the definitions that we will follow. Okay. So, what do we do once we define this, right. So, first definition, or something that will be useful to us, is the rank of a linear map. A rank of a linear map f which goes from u to v with a corresponding metric representation, which is A, which is of dimension m cross n. So, the dimension of the image of f, or the rank of f, is simply the dimension of the image of f. Right. So, again comes from some basic definitions over here, right, coming again from the column space till the image and so on. Okay. So, the first definition is the dimension of the image of F, or the rank of F is simply given by the dimension of that image of F. Similarly, for column space, I can just write that the rank of A is the dimension of the column space of A. Similarly, I can write for the dimension of the row space of A is also the rank of A, which is dimension of R of A. So, just to summarize, I have the rank of a map. So, this is my map, say this is equal to R, this is also equal to the rank of the corresponding matrix A. This will also equal the dimension of the column space, or also the dimension of column of the row space, and at best it can be of dimension m comma n. I think you can just write down a little example or the little details, but these are pretty straightforward, right. Okay. Now, what does the rank of A give me? The rank of A gives me the number of linearly independent columns or number of independent rows of A. Okay. Right. Okay. Now, just to summarize, right. So, if or just to carry forward of those definitions, a matrix of full rank is of full rank if the rank of A is the minimum of m cross n. So, if say I just take a 4 cross 5 matrix, if the rank of A is 4, then I say it's full rank. If it's 3 or 2 or whatever, then it's rank deficient. That's what the next statement says. This is again straightforward to verify that the rank of A is the rank of A transpose. Nothing really to work out here, but you can just substitute here and check for yourself. Lastly, a n cross n square matrix is invertible if it is of full rank. We would have learned this in some form or the other in one of our earlier courses. And lastly, an interesting property is if I take two matrices and multiply them by each other of A times B, the rank of it is the minimum of the rank of A and the rank of B. Okay, so let's quickly do a bit of a proof for this. So, let me take a matrix A and a matrix B, right. So, each matrix will have a set of its rows and columns and rows and columns and so on. So, I can write this as A with, say let us see B's are this, the columns of B's can be written this way. So, this will give me A, B C 1, A 2, so on till n. Okay. Now, if I take an element here or this or any one of this, so each A multiplied with some ith column of B will be some kind of a linear combination of columns of A. Right. I think that should be easy to check, and therefore, every column of A, B, this is every column, this is a linear combination of A. Now, if you follow the basic definitions, the column space of A times B will follow this. And this implies, if I look at the rank of A times B, will be at first less than or equal to the rank of A. Okay. Now, again I come back to this and say, well, okay, let me erase a part of this. So, again let me look at the product A times B, right, and then every row of A times B is a linear combination of rows of B, right, and then following similar arguments as before, I can get this inequality here, which implies that rank of AB is less than or equal to rank of B, and therefore the result follows, right, combining this expression and this expression, that if I have two transformations with their metric representation as A and B, the product of the rank is the minimum of rank of A and the rank of B. Okay. Now, what is the nullity of a matrix? So, we spent some time looking at what is the rank of a map or the rank of a matrix, which is a equivalent representation of a linear map. Okay. So, the nullity of map F, which again goes from U to V with a metric representation of A of certain dimension m cross n, is a dimension of kernel of F. Okay. So, again this is not really difficult to check, that the nullity of F is the nullity of A is, okay, by definition the dimension of kernel or the dimension of the nullity of A. So, nullity is 0 if and only if the null space contains only the 0 vector, right. The 0 vector here maps to the 0 vector there, nothing else maps to the 0 vector on the other side, right. And of course, so if you remember some of our undergrad training on matrix algebra, you can say the rank and the nullity of a matrix can be determined from its row echelon form. So, later if we get some time, we will spend some time revisiting those of how to derive the echelon form given a certain matrix, maybe during a tutorial class. Okay. So just to brief before that, I think so the definition or how a echelon form goes is when it satisfies the following conditions, right. The first non-zero element in each row called the leading entry is 1, right. So, it is a 1 here, a 1 here, a 1 here and a 1 here. Okay. So, the second rule says that each leading entry is in a column to the right of the leading entry in the previous row. So, for example, I have a 1 here. So, the next one can occur only in the second row, and if there is a third one, it can only occur here and nowhere else. It can occur maybe here or nowhere else, not here or not here. So, of course, we will leave the derivations for later, but okay, what do we do with this form? So, the rank of a matrix is equal to the number of non-zero rows in its in this echelon form. Okay. So, this leads us to one of the fundamental theorems that we will require through the course of into deriving concepts on controllability or observability. So, what does the theorem say? So, given a linear map F which goes from U to V with a corresponding metric representation A as always, the rank of F plus the nullity of F is the dimension of U, or the rank of A plus the nullity of A is equal to n. So, what is the dimension? So, if I in this case U is Rn, V is Rm, and I have a map F which has a matrix representation of A. So, rank of F plus nullity of F has the dimension n. Okay. Now, we will just quickly do a sketch of the proof. Okay. So, I can start from F going from U to V with dimension of U is n, dimension of V is n. Okay. Now, let us assume for simplicity that the dimension of the kernel of f is some number k. It could be 0 also, right. So, that does not, so k which will be less than or equal to n. Okay. And let us say that the difference is such that k plus r equal to n, or we define a quantity r which is n minus k, which can also be 0 or any value between 0 and n. Okay. Now, what I know is that the kernel of f is a subspace of R n. Because the kernel is defined here in U. Okay. Now, if this is a subspace, it will have a certain basis of dimension k. So, I will call that, say, let us say E1 till Ek be the basis for kernel of this map F. Okay. Now, this U is an n dimensional space. So, let us say that the total basis of that would be E1 till Ek plus 1 till En, right. This is a basis for U. Now, what is to be proven here is if this is the basis for the kernel, that the remaining is a basis for the image of f, right. So, we have to prove f Ek plus 1 f En is a basis for the image of f. Because okay, why am I doing this f? Because when I am talking of image, I am already in this in Rm, I am already in this subspace V, right. So, what is to be proven now is that f of Ek plus 1 till f of En is a basis for the image of f. Okay. So, just assume that for some x in U, there is a corresponding y in V such that f of x is equal to y. Now, x can be written as some coefficient C1 E1 plus Cn En, right. So, because E1 till En are the basis for U, and x will have some of its own coefficients or its coordinates. So, this will also include C1 E1 plus Ck Ek plus Ck plus 1 Ek plus 1 till Cn En, where n was k plus r, where k we called as the dimension of kernel of f. Okay. Now, y is equal to f of x, right. Now, how will this numbers or this vector transform under f? Well, this is f, this entire thing is C1 E1 Ck Ek plus all the way till Cn En. Okay. I will just expand it. Since this is a linear transformation, I can write. So, similar to what we did yesterday in change of basis, f E1 C k f e k plus c k plus 1 f e k plus 1 plus c n f e n. Okay, now what do we know about f with E 1 till E k? So, the assumption we made was that let E 1 till E k be the basis for the kernel of f, right. So, this all numbers here will disappear, right? They will just be 0, because all these appear in the kernel of f from E 1 till E k. So, what we are left with is C k plus 1 f e k plus 1 plus c n f e n. So, here I am just looking at the image of this vector x. Okay, now what is to be shown is that this f e k plus 1 till f e n that these vectors they span the image of f, right. So, we also in a way have to ensure that that they are not linearly independent, right. So, to preserve the dimension. So, let us assume for a moment that they are actually linearly independent, right, which means that so this vector representation C k plus 1 f e k plus 1 all the way till C n f e n is actually equal to 0. Okay, now since f is linear, I can write this as f c k plus 1 with e k plus 1, which are the basis vectors. C n e n is also equal to 0, right. Now, going by the definition of the kernel, this would suggest that this particular vector is an element of the kernel of f. Okay. Now, what do we know about elements of kernel of f from starting from the definition when from over here, that well they can any element can be written in terms of its basis E 1 till E k. Now, I claim that they can also write it in terms of E k plus 1 till E n, which means that there is some kind of a linear dependence between E 1 till E k and E k plus 1 till E n. Okay. Now, what are these E 1 till E k plus 1 till E n? So, these were the basis for R n, right, which means that this actually is a contradiction, that I cannot write it in this way, right. So, E 1 till E k plus 1 till E n are actually linearly independent, right, and therefore, this assumption that well can I write assuming that this vector can equate to 0 is a contradiction, because E 1 till all this E 1 till E n are the basis of U or basis of R n, and thus supposed to be linearly independent. So, what we can say is that this can never be 0, right, and therefore, f e k plus 1 till f E n are linearly independent, right, and thus form a basis for the image of F, right, and therefore, the dimension of this image of F is R, which proves the claim of the theorem, right. So, that the dimension of the kernel plus the dimension of image is n, where n is the number of columns of the E matrix. So, as a corollary, if I look at in terms of the matrix A transpose, then well, it's obvious now to verify that the rank of A transpose plus the nullity of A transpose would be m, where m is now the number of columns in the A matrix. As a summary, so if I have again a matrix A of dimension m cross n, the column space is a subspace of Rm, the null space is a subspace of Rn, row space is a subspace of Rn, the left null space is a subset of Rm. So, the column space of A would be of dimension R and n minus R. So, together they will give me the dimension n. Similarly, here I am looking at A transpose. So, R and m minus R would give me m, right, just to summarize what we have so far. Okay, so the last theorem that we will do in this module is something that relates the null space to the row space and the null space of A transpose to the column space. Okay, so first let us quickly see what this symbol is. So, this symbol is usually called as the orthogonal complement. Okay. So, mathematically what it means, so given a vector space V, so its orthogonal complement would be all x. So, this V is a subspace of Rn. So, V perp as they call it is all x in Rn such that x transpose times z equal to 0 for all z belonging to V. Okay. So, the orthogonal complement V perp of V of a linear V is a linear subspace of Rn is the set of all vectors x which are orthogonal to every vector in V. Mathematically it just means this, right, that x transpose of z equal to 0, where x is in the perp and z comes from V. Okay, now let us see the proof of this. So, I just write it a little different. So, these two statements can be equivalently written as the image of A is the kernel of A transpose with the orthogonal complement. Similarly, kernel of A is the image of A transpose with the orthogonal complement. Okay, so this equality should be okay, right, between these two statements and these two. Okay, so we'll just prove one of this. So let's assume that there is a vector x belonging to the image of W. So, which means that x is in image, sorry, not W, it's okay, there it is. Okay, assume that x belongs to the image of A, which means x in image of A implies there exists some vector eta which is such that this x comes as A multiplied with this eta. Similarly, if I take a vector z which comes from the kernel of A transpose, this would mean that A transpose times z equal to 0. Now, look at these two combined. So, if I take z transpose and multiply it with x, I get the following, right. So, I have z transpose A times eta. Okay. Now, this is also necessarily equal to 0 because of this A transpose Z equal to 0, which will also mean that Z transpose of A is also equal to 0. Okay. So, what does it mean, right? So, x, this vector is orthogonal to every vector in the kernel of A transpose. Okay. So, we have not proved yet, right. So, what this actually means that x is orthogonal to every vector in the kernel of A transpose, which mathematically which means that x belongs to the kernel of A transpose with the orthogonal complement, right. So, x is orthogonal to every vector in kernel of A transpose, which means x belongs to this space here, right. Now, where does x come from? X is the image of A. So, therefore, if I take the set of all these x, I can only say that, okay, let me write it in a box here, that this image of the image of A is a subspace of the kernel of A transpose with the orthogonal complement. That is all I can say. I still cannot prove the equality. Okay. So, to prove equality, we will invoke the rank nullity theorem, which we had seen in the previous slides. Okay. So, what we know so far is that the image of A is satisfies this, the kernel of A transpose with the orthogonal complement. Okay. Now, to show that these are actually equal, we need a couple of more steps. So, first thing we know from the rank nullity theorem is that dimension of kernel of A transpose plus dimension of the image of A transpose is M, because A here is a M cross n matrix and A transpose will be n cross m. So, the dimension is the number of columns. Okay. Second thing that is if you are writing the first time and is easy to intuitively it should be clear, right. So, dimension of kernel of A transpose plus dimension of the kernel of A transpose with its orthogonal complement is also equal to m. Say like m equal to 2, if the kernel of A transpose looks like 1 0, then this orthogonal complement will necessarily be 0 1, and hence the total dimension is like 2. Similarly, if I have kernel of A transpose in a 3-dimensional space looks like this, then its perp or its orthogonal complement will have either 0 1 0 or 0 0 1 or any linear combinations of these two. I can just swap these two and say if this is the kernel of A transpose, then this will be in its orthogonal complement. So, this is like intuitively clear. So, from these two things what we can conclude is the following, that the dimension of image of A is also the rank of A is also equal to the dimension of image of A transpose. This is also equal to the dimension of the kernel of A transpose with the perp, right. So what I want, so what I know so far is these two, that the image of A is a subspace of the orthogonal complement of the kernel of A transpose, and additionally what I know is that these two spaces are such that the dimensions are equal, right, and this is possible if and only if there is a strict equality between the image of A and the kernel of A transpose with its perp. Okay, that's one part of the proof, and the second part of the proof is kind of straightforward from this. As a little simple example, so let's take a matrix A which looks like this. It says 1 0 0 0 0 0. Okay, so the null space of A would be, well, the span of these two vectors 0 1 0 0 0 1, or any linear combination of these two elements. The null space of A transpose would look like 0 and 1. Okay, so what it means is that you take A, this matrix A, and multiply it by n of A, then you get a 0. Similarly with the A transpose, where A transpose looks something like this: 1 0 0 0 0 0. You may, since there is 0, you may as well get rid of this row, and then if you so you can easily check that this is the null space of A transpose. Okay. Similarly, the column space C of A is the line which passes through 1 0, okay, and the row space is also a line which passes through 1 0 0 or 1 0 0 transpose. Okay. Now, if you go back to the theorem statement, it says that n of A is in the orthogonal complement of R of A, right. You take an element from n of A, and that it will essentially be in the orthogonal complement of R of A prime. So this is R of A. Take any element from here, from n of A, say take say 0 1 0 1 0 0, I get 0. Similarly with the second element also, right. So the definition here is that x transpose of z should be 0. Another important thing or interesting thing to note here is that I take the perp and I take the perp again, I get back my original space. Similarly, you can verify this also, right, that the null space of A transpose is in the orthogonal complement of CA, right. So take this and multiply 0 1 from here and 1 0 from here will give you 0, right. So this, the relation between these two holes and the relation between these two holes. So that is a little illustration of a theorem which says the following. Okay, so how do we visualize these four fundamental subspaces? So we have the row space of A, the column space of A, the null space of A, and the null space of A transpose. Okay, so what do we have as relations? We know the following, that well, the dimension of the row space is R, it is a subspace of Rn. Okay, so row space, it is a subspace of Rn, it is of dimension R. Then I go to the null space of A, which is also a subspace of Rn and of dimension n minus R. Okay, so this is the null space of dimension n minus R, and together the row space of A, or the dimension of the row space of A plus the dimension of the null space of A is Rn. The fundamental theorems which we had earlier, right. So this one, the rank of A plus nullity of A is equal to n. Okay. Now similarly, I have the column space of A which is a subspace of Rm. I can denote it as the column space of A of dimension R is a subspace of Rm, and similarly the null space of A transpose is a subspace of Rm now, and it is of dimension m minus r, right. So, this is where this sits. Okay. Now, so what does this mean? So, the null space of A means the following. So, if I take a vector x n which belongs to the null space of A, the map A will take it to the origin. Okay. Similarly, x r via this transformation A will go into the column space of A of dimension r, and so on. So, what we also know is the following, that the null space of A and the row space of A are orthogonal to each other. Okay. Then the null space of A and the row space of A are orthogonal subspaces to each other, and together they will again be of dimension n. Similarly, with the null space of A transpose and the column space of A are also orthogonal to each other. So, the dimension of this plus this would be m. So, that is a little pictorial representation of this, and also for what does this map show us. So, if I take an element xr from the row space and element xn from the null space, it will still map to here. So, which essentially means that A times xn is 0. So, this is rewriting these two equations together. Okay. So, that is a little visualization of the fundamental subspaces given a matrix representation of a transformation which is essentially of dimension m cross n. Okay. So, what we did here is in this lecture is to define fundamental subspaces of a matrix. We had the concepts of rank and nullity of a matrix. We did a proof of the rank-nullity theorem and also the fundamental theorem of linear algebra together with its geometric visualization. So, the next module we will talk of change of basis. We will do lots of things on properties of matrices, eigenvalues, eigenvectors. We also look at invariant transformations, subspaces, and also end with similarity transformation, and how these transformations will make matrix computations a little easy further. So, that is coming up in module 3 or the lectures of week 3. Thank you.